So we're going to be looking at one of the last questions in the electric field section on the note guide. And so today's learning goal here is to use the variation technique. So this is just a technique we've done a few times to extrapolate the changes made in the motion of a particle, an electric field, when some of the initial conditions are altered. Basically, the idea is to set up a ratio or relationships between the initial and final conditions and follow how those changes relate to the particle's final motion. Okay. All right. So here, looks like we've got a positive charge Q. It's got a particular mass. Is released from rest in a uniform electric field. Okay. And is directed along the x-axis there. It impacts the far plate with a velocity of v. How much larger or smaller would the impact velocity be if the charge, mass, and field strength were each halved? Oh, all three of them. Okay. So basically, it's like how much larger or smaller would the impact velocity be? So what we want to do here is the final answer is going to be essentially V final over sort of V initial equals some kind of number, hopefully, right? And essentially, let's say you get a 1 here. Then the V final and the V initial are the same, so it wouldn't be any larger or smaller. If you end up getting a 2 here, then that means the final velocity would be twice as large as the initial velocity. Okay. I'm saying final and initial. You know what I'm actually going to do is I'm going to change these to a 1 and a 2, right? Because I'm going to call this 1 for the first scenario and 2 representing the second scenario. The second scenario is where all of the all of those measurements are chopped in half. So the mass is half, the field strength is half, and the charge is where is it? Charge is half as well. Yeah. Okay, so now that we know that that's the case, all right. So it depends on what number we get over here, and that number is going to be the answer to the question. All right. So basically what we need to do is we need to essentially sort of get V2 and V1 sort of isolated, all right, and stuck into a ratio, all right? And there could be a bunch of stuff over there, and then we just got to do some simplifications, things like that. Well, I'm going to write down a couple of scenarios. I'm going to say that Q1 is equal to Q2, right? And I'm going to say that M1 is equal to M2, and I'm going to say that field strength 1 is equal to field strength 2. And these should be vectors here as well. I probably dropped the vector symbol in some of my work. These also should be vectors as well. But I'm probably going to drop some of these vector symbols just as I move through here to kind of not clutter up the page. Now, excuse me, sorry. What am I going to be doing here? Notice all of the final conditions are chopped in half, right? So we basically can write the following, right? They're not equal, right? They are actually equal to 2's here, here, and here. Okay? Because the final, or in the second scenario, the charge 2 is half of charge 1. So if you want to set them equal, you can say that charge 1 is equal to 2 of charge 2's, right? And so that's basically what this statement here says, okay? And so there we go. We're going to go ahead and take a look at that. So now what I want to do here is I want to basically kind of think about how am I going to actually even in the end figure out the velocity with which the particle hits that other side. Okay. Well, what I'm going to do is I'm going to go ahead and set this up in terms of energy. All right. And so I'm going to set this up in terms of the energy, right? So the electrical potential energy, right, should equal the kinetic energy that the thing ends up getting, okay? Now, the electrical potential energy is just going to be equal to, now we're talking in a uniform field. So where were these formulas? They're way up here. Did I move through these? This was a non-uniform over here. This was also a non-uniform. Did I go over the uniform electrical potential energy field? Here it is. It shows up in this formula here. The change in electrical potential energy is the delta V Q, right? Delta V Q. So let me write that down. And then I'm also going to write down this guy, the electrical field strength. The change in electrical potential energy is delta V over Q. And then my field strength is going to be delta V over R. Okay? And essentially, what I'm going to do here is sort of play around with some of these things. So this is essentially going to be the electrical potential energy that the thing uses as it moves through the field. Okay. Now I'm going to solve for delta VR over here. I'm going to solve for delta V, and I'm going to get the following formula that delta V is field strength times R. All right. And so, therefore, my electrical potential energy is, or my change in electrical potential energy is going to be field strength. It's going to be field strength times R over the charge of the particle. And just to sort of reiterate this change in energy is electrical potential energy final minus electrical potential energy initial, right? And this is ERQ. But the final electrical potential energy is 0, okay? And so basically what we can kind of say is this is the initial electrical potential energy that the thing had. The reason why it's 0, because it goes through the entire field here, okay? And then also our change in kinetic energy, since it started from rest, because it says it's just released from rest, it means my kinetic energy was 0 as well, all right, at the beginning. And so basically what happens, I had 0 kinetic energy and a bunch of electrical energy here. And then over here, I have all kinetic energy and no electrical energy here. And so as a result, you can basically just sort of quickly set those guys equal to each other because all of the electrical energy turns into kinetic energy, okay? So as a result, my electrical energy formula is going to get substituted in right here, all right? And basically, I end up having field strength R over Q should equal 1/2 mv squared. Okay? Now, what I'm going to do is I'm going to solve for V in this thing. All right? And so I'm going to go ahead and multiply it by 2, divide by m, and root it. So it's E R over Q. Did I divide by m? I multiplied it by 2, and I rooted it, and that should be the velocity with which the object hits the other plate. Okay? It's 2 field strength radius over charge of the particle times its mass. Okay, let me just double check to make sure I didn't screw something up there. I think that looks okay. This is now basically our working formula. All right. And now what we're going to do, that's all of the sort of the kinematic, the electricity section there. Now what we want to do is take and throw this thing in. We basically want to throw this yellow circled formula into this thing way up here, which is basically how the answer gets solved. All right. So maybe what I'll do is I'll move it down here so we can see a little bit better. So basically my V2 over my V1 is going to be the square root of 2 field strength 2 R over Q2 mass 2. Why am I using 2's there? Well, because to figure out the velocity in the second scenario, I've got to use the field strength in the second scenario, the charge in the second scenario, and the mass from the second scenario as well. All right. And then likewise, I need to, in order to determine this, I need to do 2 field strength first scenario radius over charge first scenario and mass first scenario. Oops, that's supposed to be a 1 right there. Okay. There we go. Let's throw down a 1. Okay, and now a lot of people would cancel these roots right now. Don't do that because there's no roots over here. You can't cancel roots like that. You can cancel roots if they're on either side of the equal sign. Notice my equal sign is here, not in between these guys. Okay, so don't cancel those roots. Notice my R doesn't have a subscript because the R is the distance between the plates. And if you read the question, the only thing that's changed is the charge, the mass, and the field strength, not the distance between the plates. And so therefore, the distance between the plates was R in the second scenario, and it was R in the first scenario. So I've just left it an R there. Okay. And now algebraically, if you take a look at some of this stuff, these R's cancel. Turns out these 2's are going to cancel. Okay. And now what I'm going to do is I'm going to replace field strength 1 with 2 times field strength 2, right? So I'm going to do this. I've got field strength 2 over charge 2 mass 2. Divide over field strength 1. Oh, but wait, field strength 1 is actually 2 times field strength 2, right? So I'll go ahead and write a 2 there. 2 times field strength 2. Charge 1, which should go right here, and mass 1, which should go right there, are both also likewise 2. So I would use these formulas up here as well, which I just halfway erased. So this is going to be 2 charge 2, 2 charge 2, 2 charge 2, and 2 mass 2. Okay? And now, algebraically speaking, this cancels all of these variables, cancel with all of those variables, but the only thing left are the 2's. So these 2's actually hang out. This guy cancels with that guy cancels with that guy, and that guy cancels with that guy. And I'm left with the square root of 1 over the square root of 2 over 4. Okay? which is actually the square root of 4 over 2, or the square root of 2. Okay? And so basically, to summarize, V2 over V1 is the square root of 2. And so, therefore, the velocity under the second circumstances is the square root of 2 faster than the velocity under the first scenario or first circumstances. And another way of looking at that is to take this and do V2 equals the square root of 2 V1. And you can kind of see that that makes, or that's what's going on there. Okay. Anyway, so that was a pretty fun question. Go ahead and take a look at similar questions like that.